I remember the first time I heard that the simple act of counting 1, 2, 3 actually needs a formal proof.
Right.
A logical proof to stand up in mathematics. It just sounds completely absurd, doesn't it? We just know how to count.
We do. But in the late 19th century, foundational thinkers, well, they decided intuition just wasn't enough. Before Giuseppe Peano formalized his axioms in 1889, arithmetic felt intuitively correct, sure.
But it was missing something.
Exactly. It lacked that rigorous, watertight structure of, say, geometry. So our mission today is a deep dive into the Peano axioms.
The 9 simple rules.
The 9 simple rules, built on the work of Peano, Dedekind, and Grassmann, that provide the bedrock for all the natural numbers, what mathematicians call math BBBO.
Okay, so let's unpack this. Peano's system, it really only relies on 2 things, right?
That's true.
A starting point, the constant 0, and this thing he called the successor function.
We could call it the step-up function to make it
Here,
clear.
I like that, the step-up function.
That function is the engine. The first 8 axioms basically just define how that engine operates. Axiom 1 says 0 is a natural number.
Simple enough.
And axiom 2 says if you use that step-up function, you always get another natural number. The system is closed.
So it's a nonstop chain reaction. But what prevents that chain from looping back on itself or getting tangled?
Right, that's a key question. And that's where 2 crucial constraints come in. Axiom 8 states that 0 is not the successor of any other number.
It's the absolute start, the unique starting point.
Exactly. And axiom 7 ensures the step-up function is injective.
Meaning
Meaning if you step up from number nullers and you step up from number nor and you land on the same spot, then nuller never had to be the same number to begin with.
I see. So every number has one and only one direct predecessor. That prevents the number line from branching or...
Looping back on itself. You got it.
So we have the start, that's 0, and we have the connection, the step-up function. But how do we know we haven't built some faulty structure with extra numbers we don't want?
That is the most powerful rule of all. Axiom 9, the induction axiom. It guarantees no junk.
No junk.
The source uses a great analogy. The first 8 axioms, they define the dominoes and how they're connected.
Okay.
The 9th axiom says that if a property holds for 0, and if whenever it holds for a number 9, it also holds for the next number, then
Then it has to hold for every single natural number.
every single one. It proves the only numbers in our set are the ones you can get to by starting at 0 and just repeatedly taking that next step.
So the only tools we really need are 0 and this single rule. The next one is.
And that single rule is what lets us define all of arithmetic recursively. Take addition. It's defined by just 2 simple statements.
Which are?
First, a plus $, and then a plus the successor of $, is just the successor of a plus b.
Okay, so this is where things can get a bit tricky for me. How do we know that addition, defined that way, will always be commutative? The a plus b is the same as $1 plus $1. Doesn't that need its own proof?
It absolutely does. And that's the power of that induction axiom. We use induction to prove all those properties you expect.
Like commutativity, associativity.
Yeah, all of them. They all flow logically from just those 9 foundational rules. The whole structure becomes truly self-consistent.
Before we get into the challenges that came after this, let's take a quick moment to thank our sponsor. This deep dive is sponsored by Embersilk.
If you need help with AI training, automation, or even just uncovering where agents could make the most impact for your business, you should check them out.
You can find them at embersilk.com for all your AI needs.
So we've established that the Peano axioms give us this beautiful, solid structure for counting. But this is where the story gets really interesting.
Right.
Almost immediately, mathematicians like Henri Poincaré started asking, is this system actually consistent?
You mean, could you use these same rules to somehow derive a huge contradiction, like proving that 0 equals 1?
Exactly.
Yeah.
David Hilbert, he took that challenge to the highest level. Proving the consistency of arithmetic was his famous second problem in 1900. He wanted absolute certainty.
And then came Gödel.
And then, 30 years later, Kurt Gödel delivered what felt like a devastating blow with his second incompleteness theorem.
It was a huge deal.
It showed a fundamental boundary. If Peano arithmetic is consistent, you actually cannot prove its consistency from within the system itself. There's a limit to what its own rules can know.
But that wasn't the final word, which I think is a great testament to our ability to, find solutions to these deep problems.
Absolutely, the progress just continued. Gerhard Gentzen, in 1936, he later provided a complete proof of consistency. Confidence was restored.
So how did he do it?
He just had to use more powerful tools, specifically something called transfinite induction, which exists outside the limits that Gödel had identified. so mathematicians could breathe a sigh of relief. The foundation was sound.
And that assurance, that leads us to a really inspiring final thought.
It does. Dedekind proved that the original Peano axioms are what we call categorical.
Which means they only have one model, right? One unique version of the numbers.
The standard natural numbers you use every day, 0, 1, 2, 3, and so on. But here's the mind-bending twist. If you weaken the logic just slightly to a first-order version of Peano arithmetic, a result called the compactness theorem implies. Well, it implies the existence of non-standard models.
Wait, hold on. So the same fundamental rules that define simple counting can also define, what, infinite chains of other alien numbers that follow all the same rules?
Yes. They aren't our familiar naturals, but they satisfy the exact same axioms. It just shows the sheer richness and depth of mathematical logic. Even the simple act of defining 1 + 1 = 2 opens the door to possibilities far beyond our everyday experience.
Proving that the search for mathematical foundations only expands our universe of knowledge. What a thought.
Indeed.
If you enjoyed this deep dive, please subscribe to the show.
And hey, leave us a 5-star review if you can.
It really does help get the word out. Thanks for tuning in.